Sorry about the. Sorry about that. The one time, so I just recently upgraded to OBS, and it was behaving so well over the last couple of weeks, or last week or two or so, where it would never disconnect my audio. But now is the first time. First time I don't check it, of course. That's the first time that it disconnects the audio. So sorry. To update everybody online. Yep, there we go. We are reviewing the Gaussian elimination, and these were the questions were about swapping that pivot row. And that pivot row, basically, here's the ith row, right? And what you're looking at is this one, and then you're comparing it to all the other ones down here, and you're finding that row with the highest magnitude here, right? The highest magnitude because we're using absolute value here, right? Absolute value, absolute value, absolute value, absolute value. We assume that, well, I is going to be the best row for the pivot, right? And then we go through and we find the through rows I plus 1 through n, the one with the highest magnitude, right? That's why we're running from J here, J, and then pivot row versus pivot row, right? But we're only looking at elements in the ith column, okay? Then once we've found that, we swap rows I and pivot row. That's what this is doing, okay? And again, it just swaps this guy for this guy, this guy for this guy. So it swaps these two, swaps these two, swaps these two, etc. That's all it's doing. Before making them 0, because this is where you end up making them 0, right? This is where you 0 them out, right? The point of swapping them is that, well, again, it's not really relevant if you're using a multi-precision programming language like Python. You want to reduce, if you were using like C or C++ or something like that, by going with the highest magnitude, you would end up reducing the amount of round-off errors in your analysis. Like if you only have a 64-bit number to represent this stuff. If you continuously divide by a large number, and then multiply by a small number, divide by a large number, then eventually all these numbers get the errors compound, and everything ends up 0 or some unexpressible number. It's not all that important for Python. You'll probably, especially with the examples or the test cases we use, you're probably gonna, if you took out rows 3 through 8, I'm sure that you would probably end up with the same answer if you're using Python. Has anybody tried that? You didn't have these rows? Yeah. So you didn't write 3 through 8 at all,
no,
right?
I tried, and then I got confused swapping. I was like, I'm just gonna try it.
Yeah. So Python, it'll work because if you need more bits, here's more bits. Yeah.
I think for one of them, it got like 2 to the -16 instead of 0.
I mean, that's essentially 0. Yeah.
That's essentially 0.
Yeah. That's close enough.
So is that on the gray if that happens?
Yeah. I mean, I'm just going to look and see if they're close enough. Definitely need to make sure that they're ordered, because swapping 2 columns is a valid operation, but that means that you're swapping the variables, and you need to swap them back in your solution, right? But none of the swapping columns is not used here at all, right? Run this part? Or, oh no, I mean, if the output looks the same, all I'm looking at are the numbers. Right? The other reason that you might want to do this is so that, in an inconsistent system or an indeterminate system, that last row, or you're moving all the 0 rows down to the bottom by doing this pivot here, right? You're just delaying the division by 0. As you might have found, if you ever do divide by 0, right here, because that thing happened to be 0, that's either an indeterminate or an inconsistent system. And that's when you need to report that, because you're dividing by 0 right there. Right? Yeah.
I think what I did was I took the last for loop out of, well, not the 0 out part out of the for loop. So.
Oh, like you might have put it inside here or something like that?
I took it like out of the biggest form.
Oh, yeah, you definitely can't do that. That's
Yeah,
doing,
can't do
that's when one iteration of Gaussian elimination.
that.
So you definitely need this outer for loop here because you need to do it for all rows, except for the last one, right? Does that answer all the questions? Okay, go ahead. Uh-huh.
Is there any sort of pseudocode for like the second half of that problem?
Second half.
Because
Like generating a code word?
well,
Or,
isn't it like first you build a tree, right?
right,
The pseudocode is for it.
right.
And then from there you have to like you have to get like the codes of the zero
Okay,
all that. And, like,
so
The
there's
tree
also
traversal part?
yeah.
tree traversal? Okay.
There's also like the math part of it that I didn't totally understand either because the example is
Huffman. All right, so let's go ahead and use this tree and let's develop some pseudocode here. So the first question to ask yourself is, do you have immediate access to the leaves or not in your implementation? If you do, I'm just asking. You could have written it so you don't. You could have written it so you do.
what do you
You could change it so that you keep access to the leaves. Like for example,
think that is the or
not is leaf, but if here's our binary. This is our BST. This is the binary search tree implementation, right? If I had, say, on our a list of nodes that are the leaves of some tree I built, right? So leaves, right? There we go. And one thing that you could do is before you even build the tree, what could you do? Once you've built all the leaf nodes, what do? Put them into an array, or a list, excuse me, with leaves, right? So to do, before building the tree, store all leaves in leaves, right? So that should be straightforward, right? Yes? No? Oh, here. Node foo, or not, I can't do that.
You don't have to name them.
Key, parent, left, right. So here's A is equal to node and key parent, what's the key? Okay, key, A. I just created a node that has A in it. B is equal to node B, right? Right? And then I would throw those into my heap, right? I would need, that's not all I need, of course. I would throw those into my heap, right? So to do, throw A, B into the heap, right? But also, put them into your leaves, right? Because they're going to be leaves, right? Leaves dot append A, leaves dot append B. And now I've got a list of leaves, right? Right? So let's outline this. For each leaf, right? Compute the code word. All right? So start at the leaf. Start at the leaf. At this point, let's go ahead and switch over to a visualization of this. Let's start at this leaf. How do I find the code word? I traverse up to the root. Right? And what was the code word corresponding to E? 100. Equivalently, you could just go ahead and reverse that. It'll be an equivalent code. Right? There are a exponential number of equivalent codes. You're good to go. Right? So you could go 0001. Right? So what would the pseudocode for that look like? Right? Current, you start at your leaf node, right? While current is not equal to the root, go to its parent, right? But as you're going up, what do? You have this string here that you start out with an empty string. And as you go up, if current is a left child, then prepend 0. Otherwise, prepend 1. Right? That's the kind of the outline, I should say. Does that help? Yeah.
But, so, using the heap thing, so the heap itself doesn't have iron search or...
No, because, well, it's not even really a heap, right? Because it's just a list that you promise yourself that you're going to treat that as a heap, right? Was that in demo? Yeah, there it is. There's nothing to stop me from doing this. After I heapify it, I can mess it up, right? I could say that h dot append, I don't know, -100, right? That should be at the top, but I put it at the bottom, right? And that's not a heap anymore. Only if you promise yourself that you're only going to insert stuff by using heap push and take stuff out by using heap pop, does the heap remain a heap? That's why it's not ideal, but that's because Python, technically Python's not, it has object-oriented programming facets, right? I mean, it has classes. It doesn't really have polymorphism though. It has duck typing. So it's like really, really weak OOP. And this exemplifies that. This is, I mean, you could design a better heap by making a class and then making private member variables. And it is a heap and will always be a heap because you can only call these methods. But the way that they design this is that, oh, we'll be more flexible. Sometimes you can treat it like a list and you can go ahead and treat it as a heap if you want to, right? And if you're, you can do whatever you want with it. You can treat it as a stack if you want, right? Because it's just a list, right? So it's more flexible at the cost of you could screw it up. But that kind of screw up is much more fundamental on a philosophical level, right? It's not like C where, oops, I forgot to clean up free up my memory, and so we've got a memory leak, right? That's a performance issue. This one is more of a conceptual issue. If you don't know what the hell a heap is, you are going to screw it up, right?
So how would you implement that? How would you implement methods that get left?
It depends on how you implemented your node, right? Is left, remember we did, am I a left child or not? Am I a right child or not? Right? You can do that, yeah. You could do getters if you want, but that's kind of, you don't do that in Python because Python doesn't have strong encapsulation, right? Def get parent, yeah, you don't do get parent, right? And that itself, you just go, if I've got a node, I just go node dot parent, right? That's why it's, that's, remember that dang it, encapsulation, yeah, it's encapsulation, right? There are 3 parts to it. It's the grouping of data, grouping of methods that act on that data, and the protection of that data. There is no protection of that data with a programming language like Python. Yeah.
So like in the pseudocode, would the like portion of it that you would store the leaves, would that be the part like at the top where you go through all the keys and you like
Yeah, that's right. I mean, if you,
all of those
where's the, there's the algorithm, all right? So insert in here, I've got a single tree node, insert into H, and then in addition, it's right here, right? Add to leaf list, right? I mean, that's what I would do. I mean, you can get more fancy and you can, for example, you can adapt this in order traversal that we did. Where is it? Delete, search. Didn't we do an in order traversal, I thought? Where the hell is it? Maybe it's just, what? Oh, okay, well there's in order. There it is, thank you, there we go. You could do the same thing with in order, right? But instead of passing in a list, you pass a string, right? And that string, if you go down left, you append a 0. If you go down right, you append a 1. when you come back up, whatever the last character is, you delete it, right? And so you can have a recursive solution here as well. And then you don't need to store them, but that's a little bit more complicated. And then you could have, instead of relying on recursion, you could use a stack instead, right? And then anytime you go down left or right, you push something onto the stack, you have this string that you're always manipulating. Yeah.
So if you did it with the heap deletion, then on Wednesday, you would have to find there's an arithmetic to find the parent. To find the parent.
Yeah, I mean, yeah, but that so if you want to, a heap is not the same thing as a tree. I mean, you're taking stuff out of the heap and then making it into a tree. You're storing your entire trees are being stored in that heap, right? With respect to the root node. Right? So that's one way. Another way would be, well, yeah, just the tree traversal algorithms. Yeah.
Once you end up with a list of leaves, can you just heapify that list to get it ordered like it shows on the expected outcome?
You could, but if you did you do the func tools? Then you don't have to put it into a heap. In fact, you don't want to put it into a heap. You probably just want to put it into here's trees. So assuming nodes are comparable, right, then you can just do what? Sorted leaves, right? Just sort it, because it's a list of nodes. And if you're comparing, now you got to be careful there, because if you are making your nodes comparable with respect to frequency, then this won't work, because it'll just sort it with respect to frequency, right? So if you want to, you can go Python sorted with key. This looks like Python 2. Oh, no, there. So there's the example. All you have to do is provide a key. So what would that look like here? Key is equal to, not the length, something like key equals, I think it would be,
So the x colon equals x dot?
I'm not sure what the syntax would be, but you need to get the character of the node. And then you'd sort it that way. Yeah. Sorry, I couldn't hear you. The same two. So here's an easy way of doing it. All right. 10 A's, 8 B's, 5 C's. Right. Keep it small. Don't grab lorem ipsum text and then do it manually. Right. Just do something very, very simple. And then keep in mind that you'll also have end-line characters, unless you go 10 A's, 8 B's, 3 C's, all as one line. Then you don't have to worry about end-line characters. Yeah.
So the output, the coding doesn't really matter, or just the compression needs to be.
Yeah, and that goes to your final question there of what is the math behind that, right? Let's see, where... let's go with this. Okay, here we go. No, let's start fresh. The math behind it is, oh, sorry. I'm looking for the tree anyway here. There we go. All right, so if this is the Huffman code, what was the average code word length? Average code word length. All right. So when you're talking about an average, you're talking about a weighted average, right? A is going to be encoded as 001. So the code word length there is 3, but its frequency is 10%. So it contributes 0.3 to the overall. B is, where is it? 101. And so its code word length is 3, but its frequency is 0.15. So it's 0.45. C, D, ... You add those all up, and you eventually get, I think it was 2.53, right? That's the average code word length for this particular example. Now in the output, we're asking what's the compression ratio, or what's the original. If you think of these things as ASCII, right, then the code word length is going to be always 8, right? Well, that's the code word length, because it's a fixed length encoding. The total size of the original file, is going to be the number of characters times 8 equals X bits. How do we report it, bits or bytes? Bits, okay, there you go. All right. Now, if in the encoding, right, then you take the average code word length, right? Let's say that that's C, I don't know, right? Then 8 minus C divided by 8 will give you the compression rate. Right? There are a couple of ways of looking at that, right? If you go to a store and you get a 10% discount, right, then it's 10% off. Right? That's what this is. Or it's 90% of its original price, right? So you've either cut it down by 10%, or the equivalent way of looking at it is it's 90% of its original size, right? And I forget which one we actually report in our output, but it's one minus the other one, depending on how you're doing it. Yeah.
So what we look for is the compression rate. The compression rate is about the same.
Well, if the compression rate is the same, that tells you that you have a uniform distribution on your frequency, meaning that it's not compressible.
If the compression rate is the same as the expected output.
Yeah, that's what I'm primarily going to look at, and then I'll do spot checks. I'll say, how long of a code word did Z get? I would expect it to be the same length. I'm not going to look at, well, was yours 11111 and mine was 00000. The thing to look at are they the same length? Right. Does that answer it? Or okay, yeah.
Which lecture did we do binary search tree?
Oh, I have. I don't know.
Was it the binary?
Yeah, 3.1 was a review. Yeah. No. I mean, I would just, yeah. I mean, if you're doing this for Huffman coding, I would just do something like this and self.letter, self.frequency, right? I'd keep track of the parent left and right, especially if you're going to do what we just suggested, right, and work your way up the tree, right? Then you're going to want the parent, right?
So you don't even need the search tree.
No. You don't need, and I mean, all these things would be nice to have, I'm sure, right? But as far as like in-order traversal, because I mean, it's kind of meaningless on a Huffman tree. You're not storing keys. You're storing structure to generate a code. Right? So search, delete, all that stuff, like you can erase all of that and you'd be good.
Your key would just be the character, or you can just name a character instead. You wouldn't need like a separate key, right?
Yeah, character, char is equal to char, equal to, you probably want to take the frequency too, right? Okay. All right. Any other questions online now that we're not muted? Sorry about that. Okay. Well, then let's talk about that binary search tree, because it can get bad, right? Let me go ahead and create a new empty binary search tree here, and let's insert, say, 10, 20, 30, 40, and 50, right? So if I insert stuff in order in a regular old binary search tree, what's going to happen here? Right. 10, 20, 30, 40, 50. It's always going to go to the right, go to the right, go to the right. Right? In other words, that's going to be a degenerative case, where our binary search tree is no better than a linear search tree. What we call those things, lists, right? It's a linked list. Right? All it's doing is going to the right, 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 next, 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 next. It's just a linked list. Everything devolves into order n, right? Because of that. So we need to find a solution for that, right? Regular binary search trees may become unbalanced. Right? The operations could degrade, I should say, degrade into order n operations, right? Because the height is order n. Right? So if you've got basically a trunk, right, that goes up and all the branches have been trimmed off, that's not a very good tree because it's going to be very, very tall, right? And tall trees don't survive unless they've got a lot of branches. So what we're going to do is we're going to come up with what's called a balanced binary solution. Is a balanced binary search tree. One that reconfigures itself if it ever becomes too unbalanced. Now, I'll preface this by saying that there are at least a dozen different flavors of balanced binary search trees. We're only going to look at 2 of them, right? I think in the book or the extensive note set, I've got red-black trees in addition, and then I mention all the others. If you just go to like the Wikipedia page on balanced binary search trees, you'll find a dozen solutions for this. The ones that we're going to look at are AVL trees and 2-3 trees. AVL trees, AVL stands for the author's names. I have no idea who they are. You can look that up if you care about their names. The 2-3 trees are actually the simplest case of what are called B trees. And B trees are used all over the place in databases. Somebody said that there was a database course right in here right before or something. They may or may not go over B trees or at least talk about B trees because that is one of the implementations that, like, say, MySQL uses. One of the basic data structures. AVL trees, the ones that we're going to look at first, rebalance themselves if they become unbalanced. Right? So what I mean by that is, let's look at a picture first of all, and then we'll rigorously define each one of these things. So let's look at that example that we just did, but on a smaller scale. Let's look at 10, 20, and 30. Right? 10, 20, 30. That's unbalanced, right? Why? Everything is skewed to the right. There's nothing to the left here, right? So what we're going to do is we're going to draw a little hill. I'm glad I have green as my default there, right? Because it's a nice grassy hill right there. Grassy hill. And what I'm going to do is I'm going to take a chain and hook it up to this thing, and I'm going to pull it over this hill. This is called a left rotation. Because there's this imaginary pivot point here where you pull it up and over. When I do that, what does it look like? 20 then comes on top of the hill. 10 has been pulled over to the other side of the hill, and 30 remains on the other side of the hill. But now it's, a little bit higher than it was. That's balanced, right? That's perfectly balanced. If you have 3 nodes in your tree, you can't get any more balanced than that. It's a perfect triangle right there, right? What do you think it looks like if it's skewed to the other side? 10, 20, 30. That's skewed to the left. We want to do the same thing, but with respect to a right rotation. And what will that look like in the end? 20, 10, and 30. But before we go on, let's think about that. Did we screw up the binary search tree-ness of it? Right? 20, 10 is on the left side, 30 is on the other side. In fact, these are exactly the same trees, right? So, did we screw up the key ordering? Nope, we're good to go. Okay. That's not the only way that it could be screwed up, though. Or skewed, I should say. Let's go with 30 at the top, then 20. But instead of going 10 over here, I'm going to go 10 over here. Oh, sorry. You're right. 10, 20. You're right. That was not a binary search tree. Right, there we go. That's a binary search tree, though, right? But it's not necessarily screwed up to the left, right? It's screwed up to it's skewed to the left. But then, if you look at this child right here, it's skewed to the right. Right? If I just did the simple rotation of what I did before, of a right rotation, what will it end up looking like? I hook my chain up to 30, and I take it over here, and everything gets pulled up, and we have 10, 30, and 20. Does that look right? That's definitely not a binary search tree. So what we have to do is we have to do a combination here. What I am going to do is I'm going to rotate left first, right, as my first step, and then 2, I'll rotate right. This is a left-right rotation. Right. So let's look at it in phases. Phase 1. We take 20 up, it's this one, this phase right here. 20 comes up and 10 goes down. And then we're still connected up to 30 here. That looks familiar. That's a skewed to the left situation, which all we have to do is a right rotation now. And this is phase 2. It becomes 20, 30, 10. Wonderful. Right. That's as perfect as it gets, right? You can't get any more perfect than that. What's the other possibility? If it's skewed up to the right, skewed to the right, and then skewed to the left. So it's skewed to the right, and then to the left. And to make this a binary search tree, this is the situation. 30, 20, and 10. Right? No, that's wrong. Oh, wait. Just reverse myself. So everything over here needs to be greater. So 10 is up here. 30 and 20. There we go. That's the correct binary search tree, right? So to correct this one, what would I do? Just the mirror image of this. A right rotation as my first step, then a left rotation as my second step. And that results in exactly the same tree, right? That the first phase here would end up with 10, 20, 30, and then a left rotation gives me 20, 10, 30. Okay. Yeah, go ahead.
What is MySQL want to use a binary search tree instead of a list?
Yeah, like internally, its data structure is a B tree, which is a binary search tree, but it's a balanced binary search tree.
Is that better than a list?
Well, yeah, I mean for searching, yeah, certainly. That's why you put an index on your database stuff so that it can maintain the ordering of those indices and do a fast binary search lookup. Yep.
Well, isn't a list ordered list also you can also do binary search? And that's also
If it's sorted, yes, you can do that, but then that requires random access. You can't do that with a linked list, for example. Right? So it depends on the type of list that you have. And then even then it's not ideal because if you've got 1 million elements and you need to maintain that ordering, but you need to insert something right in the middle, a list is not ideal, right? But a binary search tree is, because it's going to be order log n for all operations, including insert and delete. Right? Okay. Back to AVLs though, right? What we need now is a notion of when do things get skewed, right? How do I know that something is unbalanced? Okay. So the height of a node, I mean, this is where we're getting into some terminology here, right? The height of a node U in a tree, denoted H sub U, is the length of the longest path to any descendant leaf. Now, you might have seen something defined like this before, depth, right? But depth is measured with respect to the root. How, that you are at a node and you look up to the root. That's your depth. With height, it's different. You're at a node, you look down to your leaves. And that's what defines height. Right? By convention, the height of a leaf is 0. Right? Height of a leaf is 0. The height of an empty tree, by convention, is going to be -1. The height of a tree itself is the height of its root node. Okay? So let's understand this before we move on. Let me go ahead and give myself some a tree to play with here. I don't want that tree. Here we go. This one there. Okay. So let's off to the side here. Let's list their heights. Okay. Let's take some of the corner cases. The height of a leaf is 0. So what are all the leaves here? 4, 7, 50, 30. Okay. These are heights. What's the height of 5? 1. Why? Because you look at the tree rooted at 5, and then you look to any of its descendant leaves, of which it only has 1. Right? And what's the length of the path to that leaf? 1. Okay. What about 6, though? 6, 1, 2, and 1. Right? You can go to either of its leaves. If you went to this leaf, it would be of length 2. If you went to this leaf, it would be of length 1. Right? Remember, height is defined as the length of the longest path to any descendant leaf. So which one's longer? 2. Right. Oops. There we go. Now what about 8? Are there any leaves over here? Nope. There are leaves down here, and there are leaves over here. 1, 2, 3. 1, 2. And so the height is 3. Over here, 1, 1, 2. So it's 2. Over here, 1. That's just like 5. Now, what about the root here? What's its height? 1, 2, 3. 1, 2. 1, 2, 3, 4. 1, 2, 3. Right. So what was the maximum number I just said? 4. Those are the heights of that tree. One last definition, and we'll retread this when we come back. But the height gives us a notion of balance. A tree is balanced if it has roughly the same height in its left subtree as it does in its right subtree. And that's what's called the balance factor. The balance factor of a node U, denoted BF U, is the height of its left subtree minus the height of its right subtree. Okay? So since I've got the heights here, what are the balance factors? Let's go with balance factors. I don't know if we have any colorblind folks, but tell me if I ever choose the wrong colors or not, right? Balance factors. I just chose green and gold here, right? Why? Because, well, they're just contrasting, right? So what's the balance factor of, say, 4? Well, its left subtree has a height, its right subtree has a height. What's the height of its left subtree? No, it's left subtree. So I'm at 4 here. Its left subtree is empty. Its right subtree is empty. What was the height of an empty tree? -1. So for a leaf, the balance factor is -1 minus -1, which is equal to 0. Right? I can do the same thing for all of these leaves. Right, there. It gets interesting when you look at, say, when something's not a leaf. What's the height of its left subtree? 0. Minus, what's the height of its right subtree? -1. And so it ends up being +1. All right. What about 6? The height of its left subtree is 1. The height of its right subtree is 0. So that ends up being +1 as well. What about 8? The height of its left subtree is 2. Minus the height of its right subtree, which again is -1, which is going to be 3. Right. That's just a coincidence that that's the same as its height. Don't read into that. Right. What about the balance factor of 40? The height of its left subtree is 0. The height of its right subtree is 1. And so it ends up being what? -1. 0 minus -1 is going to be +1 on 80. And what about the last one here, 10? What's the balance factor here? 3 minus 2, which is +1. All you had to do is take the green numbers. That's why I asked if anybody's colorblind, right? Okay. Come up with some observations before we leave here. What if the balance factor is 0? A balance factor of 0 indicates what? A well-balanced tree. Right? If I go off in that direction, if I go off in that direction, they have the exact same height. Right? Nice symmetric tree. Right? A negative balance factor indicates skew to the left, right? Which one? A positive balance factor indicates skew to the left, right? Which one? Let's go back to our example here. Let's look at the most egregious example here. 8. It has a balance factor of 3. It's positive. That tells you it's skewed to the left. Is there any balance factor that's negative here? 2? 40, there we go. 40, right? That's the only balance factor that's negative. And that says that it's skewed to the right. This tree is bigger than this tree. It's higher than that tree. So positive was what? Left. And negative was right. There we go. That tells you how to rebalance stuff. Right? If it's too much skewed to the left, what do? You rotate it right. If it's too skewed to the left, you do what? You rotate it to the... if it's too skewed to the right, you rotate it to the left. Left, right, whatever. BA start. All right, we'll look at that in more detail on Monday. No questions online? All right, have a good weekend.